Gram-Schmidt process. Let V be an ingredient space. Let V be an ingredient space and alpha 1, alpha 2, dot alpha n be a basis of V. Now we have to find an orthogonal basis of V. So first of all, taking beta 1 equals to alpha 1 and also taking beta 2 equals to alpha 2 minus C1 beta 1 for C1 belongs to real number such that beta 1 is orthogonal to beta 2. Therefore, inner product of beta 2 comma beta 1 is equals to beta 2 का वैल्यू alpha 2 minus C1 beta 1 and beta 1. अभी beta 1 is orthogonal to beta 2, that is inner product of beta 2 beta 1 equals to 0. So 0 equals to inner product of alpha 2 minus C1 beta 1 comma beta 1 equals to inner product of alpha 2 beta 1 minus C1 beta 1 that imply C1 equals to inner product of alpha 2 beta 1 divided by inner product of beta 1. Thus beta 2 equals to alpha 2 minus inner product of alpha 2 beta 1 divided by beta 1 into beta 1. From here यहाँ पर सिर्फ C1 का वैल्यू पुट किया है. Here beta 1 equals to, we can write as alpha 1 plus 0 into alpha 2. Also beta 2 equals to minus C1 alpha 1 plus 1 into alpha 2. Therefore each element of beta 1 beta 2 of beta 1 beta 2 is linear combination of elements of alpha 1 alpha 2. Therefore linear combination of beta 1 beta 2 contains linear combination of alpha 1 alpha 2. Also alpha 1 equals to 1 into beta 1 plus 0 into beta 2. From here यहाँ से हम बोल सकते हैं alpha 2 equals to C1 beta 1 plus 1 into beta 2. Similarly from here, therefore each element of alpha 1 alpha 2 is linear combination of element of beta 1 beta 2. That imply linear combination of alpha 1 alpha 2 contains in L of beta 1 beta 2. So we have shown that L of alpha 1 alpha 2 contains in L of beta 1 beta 2 and L of beta 1 beta 2 contains in L of alpha 1 alpha 2, that is L of alpha 1 alpha 2 equals to L of beta 1 beta 2. Now let beta 3 equals to alpha 3 minus d1 beta 1 minus d2 beta 2. For d1 and d2 belongs to real number with with beta 1 beta 2 both orthogonal to beta 3. Therefore inner product of beta 3 beta 1 equals to inner product of alpha 3 beta 1 minus d1 beta 1. That imply inner product of beta 3 beta 1 0, because beta 1 is orthogonal to beta 3, equals to inner product of alpha 3 beta 1 minus d1 inner product of beta 1. That imply d1 equals to inner product of alpha 3 beta 1 divided by inner product of beta 1. Also beta 3 beta 2 inner product of beta 3 beta 2 equals to inner product of alpha 3 beta 2 minus d2 into inner product of beta 2. Similarly 0 equals to alpha 3 inner product of alpha 3 beta 2 minus d2 into inner product of beta 2. That imply d2 equals to inner product of alpha 3 beta 2 divided by inner product of beta 2. Therefore beta 3 equals to alpha 3 minus inner product of alpha 3 beta 1 divided by beta 1 into beta 1 minus inner product of alpha 3 beta 2 divided by inner product of beta 2 into beta 2. Similarly linear combination of alpha 1 alpha 2 alpha 3 equals to linear combination of beta 1 beta 2 beta 3. Now continuing this process we get what? We get beta r equals to alpha r minus inner product of alpha r beta 1 divided by inner product of beta 1 into beta 1 minus inner product of alpha r beta 2 divided by inner product of beta 2 into beta 2 minus dot minus inner product of alpha r beta r minus 1 divided by inner product of beta r minus 1 beta r minus 1 into beta r minus 1 for r equals to 4 5 dot n and linear combination of alpha 1 alpha 2 alpha 3 dot alpha r equals to linear combination of beta 1 beta 2 dot beta r. Thus beta 1 beta 2 dot beta n is a orthogonal basis of V